So today I want to talk to you about differentiation, a topic that falls underneath calculus. So to really understand what differentiation is all about, first I want us to have a look at something we do already know, that is our straight line graph. So here we have our straight line graph. We know that it starts at the origin. We could even give it a name. Let's see, y equals 2x. Now this is a form of equation that we're all familiar with. This 2 here represents the gradient. And we know that the gradient is worked out by finding the change or the rise in the y value and dividing it by the run or the change in the x value. So we can represent that, and you may have seen this in your physics lessons as a little triangle symbol like this, and that just means a change in. So we can derive a formula for this gradient, and that looks like this. So our gradient is going to be equal to change in the y value divided by the change in the x value. This is a simple equation that we can use for any straight line graph, and it doesn't matter how big this change in x, this change in y is, as long as they both correspond to the same point, which is kind of this one that I'm talking about here, from the origin. That makes sense. We know how to do that. We know how to use a straight line graph to do that. But what about on a graph that looks something like this? So this is a curve. We can give this a name as well. We call this y equals x squared. Now you may not have seen anything like this before, but we know that this is just a function like any other function. If we put a value for x into there, we'll get a value for y out of here. So for 0, 0 squared is still 0. That is the origin right here. That all makes sense. But what's this got to do with gradient? Well, say I wanted you to find the gradient at that point there. How would you go about doing that? Well, right now, all we know how to do is to find the gradient of a straight line. And what straight line could correspond with that point? Well, you may have heard of this thing called the tangent. Hopefully you have. And if I were to draw the tangent to the graph at that point, it might look something like that, where it just touches at this singular point on the graph. Then I have a straight line on an axis, and so I can work out the change in the y of this divided by the change in the x, and then we shall have the gradient of this point. Hopefully that makes sense to you. What's more tricky is how on earth do we find the gradient of this straight line when we don't have any values associated with this straight line? We only have this one point to find for us, and we all know that to find the gradient we need 2 points because we need a change in the y and a change in the x. Well, this is going to require some deeper thinking. Let's think about this straight line here. To define this straight line, we need 2 points. One of the points is already on our graph, on the y equals x squared graph right here. So let's think about what would happen if I picked, let's say, 2 points on this graph, and I connected them with a straight line. Now we should be able to see that for this straight line here, I can work out the gradient because I have 2 defined points on it. Every point on this function, this y equals x squared function, is defined. I should have probably done it in a different color, yellow, but so this straight line here, we have 2 points. We can work out its gradient. Now, obviously, this here isn't the gradient at this point. We're still quite a bit off, as you can see. There's quite a large gap between the gradients of these two lines, but let's think about what would happen if we moved that point a little bit closer. Down to here, let's say, and we drew a straight line connecting those 2 points. We can see that it's getting closer and closer to our original gradient that we wanted to work out. And we could even get it closer, so somewhere like that. If I connected those 2 points, you can see as that second point gets closer and closer to our first, its gradient is going to get closer and closer to the gradient of that singular point. So how can we think about this mathematically? Well, I can name my first point x for its x value, and its y value, well, if I put x in here, I get out x squared, so its x value must be, its y value must be x squared. And that's our first point to find there. Now, if I pick my second point up here, we can see, hang on, we can see that this point is going to be a little bit more than the previous x value and a little bit more than the previous y value. By how much? Well, let's give it a value. Let's call it a little difference, so we'll use the letter d. So the x value is going to be, at this point here, the x value is going to be x plus d. Hopefully that makes sense. We've just added on a little extra d to the x value here to get to our new point. And that obviously is going to change our y value. If we put x plus d into here, we're going to get out x plus d squared. Hopefully that makes sense, and you can see where I've got my second point from. So using that information that I've just worked out, I've worked out 2 points on this graph. Now I can come up with an equation for the gradient between those 2 points. So let's see, the change in y divided by the change in x. Let's do the change in y first. That is going to be x plus d squared. Take away my original x squared. Get the right color. Okay, so that is our change in the y value. That's our second y value. Take away our first y value. That should give me the change in the y value. Brilliant. Okay, let's deal with our x value now. So that will all be divided by my second x value, which is x plus d. And we want to take away from that our second x value, our first x value, which is just x. Now hopefully you can see that this here should give me the gradient of the line that connects those 2 points. And what we said was when this point is really, really close to our first point, the gradient is going to be basically the same as at that point. Well, let's see what happens if we expand this out. So I'm just going to go to a different color now. We foil this first bracket, we'll have x squared plus 2dx plus d squared minus x squared all over, and this x is just going to cancel, leaving us with just a d on the bottom. Now hopefully you can see that this x squared and this x squared cancel each other out, and so we should be left with 2dx plus d squared over d. Okay, well, where's this taking us? We said if this d value is really, really small, then our approximation would be better and better and better. So let's think about what happens when this gets really small. Let me get rid of this down here. Let's rewrite this fraction that we have, and let's split it into two parts. So we can have this first part, 2dx, split from the d squared over d. Now hopefully you're happy enough with fractions to see that this is possible. So if we were to add these two fractions here, we'd just be adding the top line. Nothing would happen to the bottom line. And using this, we can now cancel down these two fractions. You can see that we have a d and a d there, and this d squared is going to cancel with my d there. So what am I going to be left with? Well, just 2x plus d. And I said d is getting smaller and smaller and smaller. So when this is so small, we can just not count it. It disappears when we get to that point. And what will we be left with? Simply 2x. What does that mean? I can hear you asking. So let's go back up to our graph and have a look. Well, the whole point of me working this out, this gradient out, is so I could work out the gradient of this point here. So this fraction is equal to gradient. So my 2x must be the gradient at this point. And that makes sense. I put x in, I got a gradient of 2x out. There's no numbers here, but say this point here was, let's say, 2, 4. Well, what would our gradient be? We just worked out a function to work out our gradient. There it is, 2x. So if this point was 2, 4, and I put 2 in, my gradient would simply be 2 times 2 equals 4. Hopefully you can see how I managed to find the gradient of this point on the curve. I'm going to go into a little bit more detail on how to find the gradient at points on a curve in the next video.